When you look at a McDonald's, you see a fast food restaurant. But strip away the branding and the neon lights, and you will find the most highly calibrated industrial machine on Earth. This is not a kitchen. It is a globally synchronized factory governed by strict thermodynamics, fluid mechanics, and algorithmic logistics. How do you cook a burger in exactly 38 seconds across 100 countries without a single variable of human error? You don't use culinary arts, you use physics. In this documentary, we deconstruct the hidden engineering, cryogenic preservation, and brutal mechanics behind the McDonald's empire. Welcome to Simply Explained. The foundation of the McDonald's empire was not poured in concrete. It was drawn in chalk on a California tennis court in 1940. When brothers Dick and Mac McDonald wanted to reinvent food service, they didn't consult a chef. They thought like kinematic engineers. This wasn't a rehearsal. It was the birth of the speedy service system. By chalking a full-scale blueprint of their kitchen and forcing their staff to cook invisible burgers, they calculated the exact mathematics of employee trajectories, eliminating every lost second before a single brick was laid. The McDonald brothers treated human movement as a manageable physical force. Their system was designed to entirely eliminate human friction, the unnecessary steps, the wasted reaching, and the chaos of collision. Every station was ergometrically optimized. The goal was to maintain the continuous kinetic energy of the workflow. By treating the kitchen staff not as individuals, but as interconnected cogs in a mechanical assembly, they transformed cooking into a predictable, machine-like function, reducing a Big Mac assembly to a factory operation. Henry Ford famously declared that a product should never leave a worker's hands. Long before anyone else, McDonald's applied this absolute masterclass in production engineering to organic matter. The kitchen became a literal assembly line. The product, from the specific cut of the bun to the perfect dose of sauce, was broken down into a series of repeatable, machine-like steps. They didn't just automate the cooking process. They engineered an artifact, turning the organic chaos of raw ingredients into a component of an industrial circuit. In a standard kitchen, heat is a slow, one-sided conversation. But at McDonald's, heat is a high-pressure mechanical strike. The introduction of the clamshell grill changed everything. By applying simultaneous conduction from both the top and bottom plates, engineers solved a massive thermodynamics problem: how to cook beef in exactly 38 seconds. The top plate doesn't just rest on the meat. It applies specific, calibrated pressure to ensure maximum surface contact, forcing heat into the center of the patty with industrial efficiency. Taste, in the world of McDonald's, is a chemical reaction controlled by a stopwatch. To achieve the perfect Maillard reaction, the browning that creates flavor, the grill must maintain an exact temperature of 400 degrees Fahrenheit. This isn't cooking, it's precise molecular engineering. If the temperature drops by even a few degrees, the meat boils in its own juices instead of searing. Engineers designed the grill plates with high thermal mass to resist temperature fluctuations, ensuring every patty hits the same thermodynamic peak at the exact same millisecond. The ultimate variable in any kitchen is the human. A chef can be distracted, but a machine cannot. The McDonald's grill eliminates the human factor by lifting itself automatically. When the 38-second cycle is complete, a pneumatic actuator triggers the release, stopping the cooking process instantly. There is no judgment, no feeling, and no room for error. By turning the act of searing meat into an automated mechanical absolute, they ensured that the system remains flawless, regardless of the person wearing the uniform. A French fry is biologically mostly water. When you place organic matter in a standard freezer, the slow freezing process causes the water molecules to expand into large, jagged ice crystals. These crystals act like microscopic blades, shredding the cell walls from the inside out. When thawed, the structure collapses, leaving a soggy, ruined product. To mass-produce a structurally perfect fry that can survive global transport, McDonald's couldn't rely on standard refrigeration. They had to bypass the destructive physics of water expansion entirely. The solution is extreme, violent cold. Before reaching the restaurant, the fries are routed through a massive cryogenic blast tunnel. By dropping the temperature at an unnatural, accelerated rate, the water molecules do not have time to form large, destructive crystals. Instead, they freeze instantly into harmless microcrystals. This flash freezing process completely halts biological decay and locks the water inside the intact cellular walls. They are not simply freezing a potato. They are pausing time and preserving a specific geometry. Once flash frozen, the potato ceases to be an agricultural product. It becomes a standardized industrial component. This extreme cryo state allows McDonald's to maintain an unbroken global cold chain. A batch of fries harvested and processed in Idaho can sit in a cargo ship for weeks, cross the Pacific Ocean, and arrive at a fryer in Tokyo with zero structural degradation. Cryogenics is the invisible technology that allows a highly volatile organic material to be treated with the logistical predictability of a steel bolt. Hot oil in industrial frying is not just a liquid. It is a thermal battery holding a massive charge of energy. To achieve the perfect McDonald's crunch, the oil must transfer that energy to the fry instantly. However, introducing a basket of frozen fries, essentially a volatile anti-energy block at 0 degrees, creates a massive thermal drain. The oil temperature crashes, threatening the entire process. Without massive energy capacity and standardized hydrodynamics, the fry would simmer in grease instead of searing, ruining its structural integrity. To fight this temperature crash, McDonald's deep fryers are not standard kitchen equipment. They are high-powered industrial machines. They utilize massive high-wattage heating elements and rapid circulation loops to restore optimal temperature in seconds. This isn't gentle reheating. It is a brutal mechanical fight to force heat back into the volatile bath. The precise internal geometry of the vat creates powerful turbulent currents that sweep the cooled oil past the heating elements and back into the fry basket, maximizing the thermodynamic strike needed for the perfect Maillard reaction. Standard vats create hot and cold spots, ruining consistency. McDonald's deep fryers utilize standardized mesh geometry in their baskets to facilitate specific turbulent oil currents. When lowered, the structure itself forces the hot oil to circulate evenly around every single fry simultaneously. The entire fry cycle becomes a perfectly coordinated turbulent event. By eliminating chaotic fluid variables and reducing boiling to a standardized mechanical function, they ensured that every fry, from a large in New York to a medium in London, experiences the same radical thermodynamic event and achieves the exact same structural snap. A McDonald's beef patty is not a culinary creation. It is a mass-produced structural component. To ensure that millions of patties cook perfectly simultaneously under the brutal pressure of the clamshell grill, they must possess exact, uniform geometry. The meat is not merely shaped. It is forced through heavy-duty industrial extrusion dies under immense pressure, cutting it to millimeter-precise dimensions. This strict mechanical uniformity removes biological inconsistencies, transforming raw organic material into a standardized, predictable disc designed specifically to interface with the grill's thermodynamic profile. The McDonald's patty contains 0 binders, no egg, no breadcrumbs, no chemicals. So, how does it maintain its rigid structural integrity under extreme heat and pressure? The secret is the exact manipulation of the 80-20 fat-to-lean ratio. In this system, fat is not a flavor additive. It acts as a critical mechanical binding matrix and an internal thermal conductor. Under the intense heat of the grill, the fat rapidly liquefies, transferring the thermal energy inward at high speed, while simultaneously locking the protein structures together as the patty sears. The massive challenge in the meat supply chain is biological inconsistency. To guarantee the perfect 80-20 formula millions of times a day, McDonald's suppliers utilize optical spectroscopy and inline X-ray analysis. As thousands of pounds of beef speed down the conveyor belt, they are hit by lasers. The machines analyze the molecular light reflection, measuring the exact ratio of fat to lean in real time and detecting bone fragments down to the millimeter. The system then automatically blends different batches to hit the mathematically perfect target ratio, enforcing absolute mechanical order on organic chaos. Most fast food chains treat soda as an afterthought, receiving their syrup in thin plastic bags. But plastic is a terrible insulator, vulnerable to temperature fluctuations and light exposure that degrade the delicate chemical structure of the syrup. McDonald's demanded a superior engineering solution. Their Coca-Cola syrup is delivered and stored in heavy-duty stainless steel tanks. This industrial-grade containment creates a perfectly dark, thermally stable environment, preserving the exact chemical integrity and volatile flavor compounds of the syrup from the manufacturing plant directly to the restaurant. In fluid mechanics, temperature dictates carbonation. Carbon dioxide dissolves significantly better in colder liquids. To maximize the aggressive bite of the soda, the syrup must remain at near freezing temperatures at all times. To achieve this, McDonald's engineered a specialized insulated tubing bundle. The lines carrying the syrup run perfectly parallel to lines pumping constantly chilled glycol and cold water. This creates an unbroken, active refrigeration loop from the back room all the way to the drive-thru dispenser, ensuring the fluid dynamics remain in a perfect state for maximum gas absorption. The final pour is a masterclass in applied fluid mechanics. The dispenser utilizes a highly calibrated Venturi valve, using rapid pressure drops to atomize and perfectly mix the heavy syrup, ultra-filtered water, and CO2 at the exact microsecond of dispensation. If you want to see exactly how this same Venturi effect revolutionized automotive engineering, watch our documentary on the Maybach carburetor. And if you appreciate this level of deep engineering analysis, please take a moment to like this video and subscribe to the channel. But McDonald's engineers factored in another crucial variable: the thermodynamics of ice. They mathematically calculated the exact rate at which their standard ice melts in a cup, and pre-calibrated the dispenser to release a slightly higher ratio of syrup. As the ice melts, the dilution process brings the fluid into perfect chemical equilibrium, ensuring the final sip tastes exactly like the first. In the architecture of a McDonald's burger, the bun is not considered a culinary pastry. It is an engineered structural insulator. Its primary function is to act as a mechanical container that can withstand the kinetic load of human hands while trapping the extreme thermal energy of the meat inside. To achieve this, the dough is formulated and baked into a highly specific cellular foam. This matrix of microscopic air pockets creates a perfect thermal barrier, ensuring the intense heat of the core does not transfer to the fingers of the consumer. Before assembly, the inside of every bun must pass through an industrial toaster. This is not to make the bread warm. It is a critical defensive measure. When the bread is compressed against the high-heat platen, the sugars caramelize instantly, creating a carbonized seal. This process engineers a strict hydrophobic barrier. If this barrier fails, the liquid fats from the meat and the acids from the sauces will breach the cellular foam of the bread. The structure will suffer catastrophic mechanical collapse, turning the container into a soggy ruin. Toasting is structural integrity. Because McDonald's operates on automated, highly calibrated assembly lines, the buns must adhere to strict dimensional tolerances. A bun that is 2 millimeters too tall will crush under the clamshell packaging. A bun that is too thin will fail to insulate the heat. At the factory level, optical sensors scan every single baked unit. The slicing process itself, separating the crown, the heel, and the middle club for the Big Mac, is executed to exact millimeter specifications. It is a triumph of forcing organic, living yeast to obey the ruthless geometry of mass production. In the realm of fluid mechanics, sauces like ketchup and the iconic Big Mac sauce are classified as non-Newtonian, shear-thinning fluids. This means their viscosity is not constant. When left alone, the molecular polymers tangle, and the sauce acts as a structural solid, resisting gravity. It will not flow. However, the exact millisecond a specific threshold of mechanical force or shear stress is applied, the molecular structure aligns. The solid instantly becomes a liquid. McDonald's engineering had to domesticate this bizarre physical property to ensure absolute consistency on the assembly line. You cannot rely on a human to squeeze a bottle and guess the correct volume of a non-Newtonian fluid. The solution is the McDonald's sauce gun, a highly calibrated volumetric dispenser. Operating on the same mechanical principles as an industrial caulking tool, the gun uses a heavy spring-loaded piston. When the trigger is pulled, it applies massive kinetic force, instantly breaking the sauce's structural yield stress and forcing exactly one pre-calibrated dose down to the fraction of a milliliter out of the nozzle. It guarantees mathematical uniformity, whether the tube is completely full or nearly empty. Dispensing the sauce is only the first equation. The second is its geometric distribution. The sauce gun deposits the liquid precisely in the geometric center of the bun. Because the viscosity and volume are mathematically controlled, engineers can predict the exact radial spread of the fluid when the kinetic weight of the meat patty is dropped on top of it. The sauce expands outward in a perfect circle, reaching the very edge of the bun without spilling over. It is a calculated exercise in pressure dynamics, ensuring every single bite contains an identical ratio of ingredients. The most notorious piece of equipment in a McDonald's is the ice cream machine. The public perceives it as a simple freezer, but mechanically, it is a highly complex, closed-loop bioreactor To maintain food safety without requiring daily disassembly, the machine must run an automated pasteurization cycle every night. It is simultaneously a boiler and a cryogenic freezer, forced to operate within the exact same confined space. It must independently heat the liquid dairy mixture to extreme temperatures to kill bacterial growth, hold it there, and then execute a massive thermal crash back to a freezing state. This violent thermodynamic swing is monitored by a network of highly sensitive thermistors. These sensors operate as absolute mechanical dictators. During the 4-hour heating cycle, the internal temperature must remain elevated above a mathematically strict threshold. There is zero tolerance for deviation. If someone adds cold dairy mix to the hopper during the cycle, or if a compressor lags for even a few minutes, causing the temperature to drop by a single degree, the binary logic of the machine calculates a biological risk. The pasteurization formula is mathematically broken. The moment a product leaves the assembly line, it becomes a degrading thermal asset. Packaging engineering must solve a massive thermodynamic paradox. Hot organic matter constantly releases vapor. If you seal the box completely to trap the thermal energy, the trapped steam condenses against the walls, turning the porous cellulose matrix of the bread into a soggy, structurally compromised mess. But if you ventilate the container too aggressively to let the steam escape, the kinetic heat bleeds out into the atmosphere, leaving the product cold. It is a ruthless physical battle between temperature retention and moisture extraction. The geometry of the iconic red fry container is not merely a branding decision. It is a highly calibrated aerodynamic chimney. Fries possess extremely low thermal mass and a high surface area, making them highly vulnerable to condensation. To protect the cryogenic and fryer-induced structural crunch, the packaging is completely open-topped. The tapered, V-shaped bottom wedges the fries together, creating a localized dense thermal core that shares heat. Simultaneously, the wide flared top acts as an exhaust port, accelerating the upward trajectory of the steam before it has any chance to settle and break down the lipid barrier of the potato. For the larger burgers, engineers utilize the clamshell geometry. If the lid of the box were perfectly flat, condensation would form directly above the bun and drip straight down, destroying it. Instead, the roof is engineered as a precise architectural arch. As steam rises, it hits the curved surface, condenses, and capillary action forces the water droplets to slide safely down the angled walls, pooling harmlessly at the base. Combined with specifically calculated microscopic vents located near the hinge that act as thermodynamic relief valves, the box actively manages its internal microclimate, buying the product a few extra, crucial minutes of structural survival. A commercial kitchen is an environment of intense acoustic violence. The ambient noise floor is dominated by the low-frequency rumble of heavy ventilation systems, the aggressive popping of boiling oil, hissing meat, and the constant friction of human movement. In this chaos, standard alarms would be absorbed or ignored. To ensure strict adherence to cooking times, McDonald's sound engineers could not simply make their timers louder. They had to make them geometrically sharper. They needed an audio signal designed to physically cut through the mass of ambient noise. This is applied psychoacoustics. Evolution has engineered the human ear to be most sensitive to frequencies between 2,000 and 5,000 hertz, the exact range of a baby, crying, or a scream. McDonald's calibrated their equipment buzzers to hit this exact biological vulnerability. The alarms do not play a melody. They emit a harsh, rapid, high-pitched square wave. This unnatural acoustic profile guarantees maximum auditory irritation. It triggers a mild, subconscious fight-or-flight response, compelling the employee to move instantly to shut off the alarm. The sound is not a notification. It is an engineered biological command. A modern McDonald's kitchen does not have one timer. It has dozens running simultaneously. To prevent cognitive overload, the soundscape is mapped into a highly structured audio matrix. The fryers, the grills, and the holding cabinets each utilize a distinctly different rhythm and pitch. A seasoned employee doesn't need to look at a screen. They process the kitchen entirely through acoustic data. The environment dictates exactly where they need to be and what they need to do, turning the chaotic noise of a restaurant into a precise, invisible algorithmic code that directs human kinetic energy. A drive-through lane is not simply a paved road around a building. It is a masterclass in applied spatial engineering. McDonald's architects must calculate the exact turning radii needed to funnel thousands of pounds of kinetic mass from compact cars to heavy SUVs through a narrow, curved concrete channel without causing bottlenecks or collisions. The geometry of the curbs, the placement of the order boards, and the angle of the pickup windows are mathematically designed to force human drivers into a highly predictable, mechanical flow, turning chaotic street traffic into a disciplined conveyor belt of steel. The acoustic environment of a drive-thru is brutal. Employees must clearly hear complex orders through the chaotic interference of running engines, wind shear, and street traffic. To solve this, McDonald's relies on sophisticated noise cancellation technology built into their intercoms and headsets. These systems do not simply transmit sound. They actively analyze the audio spectrum in milliseconds, applying digital filters to surgically isolate the specific frequency range of the human voice while actively blocking out the low-frequency rumble of internal combustion engines. It is military-grade acoustic isolation applied to fast food. In queuing theory, a single order point creates a mathematical bottleneck. To shatter this physical limitation, McDonald's introduced the dual-lane drive-thru. This is not just a traffic management solution. It is the physical manifestation of parallel computing architecture. By splitting the intake into two simultaneous nodes, they doubled the data input rate. The orders are processed in parallel and instantly routed to the kitchen matrix. The physical cars then merge back into a single sequential line at the exact moment their physical product is assembled, perfectly syncing digital logic with kinetic reality. In industrial engineering, excess inventory is not an asset. Storage space is a massive financial liability. McDonald's restaurants are not designed to be warehouses. They are pure assembly nodes. To maximize kitchen space, the empire operates on a brutal, just-in-time logistics model. Ingredients are constantly in motion, arriving at the restaurant exactly when the algorithmic data dictates they will be needed. This eliminates the need for massive on-site freezers and ensures that organic matter spends the absolute minimum amount of time stagnant before it is processed, cooked, and sold. A McDonald's supply truck is not simply a vehicle carrying food. It is a mobile data node in a global telemetry network. While in transit, the interior of the trailer is monitored by highly calibrated thermal sensors. The internal temperature data of the cargo is beamed directly to a centralized network in real time. If a refrigeration compressor on a truck driving through the Nevada desert fails and the temperature rises by a single degree, the system detects the anomaly instantly. The payload is not trusted to human drivers. Its biological integrity is mathematically guaranteed by satellite surveillance. The ultimate test of any engineering system is how it handles catastrophic failure. Global supply chains are highly vulnerable to weather events, strikes, and infrastructure collapse. McDonald's combats this through strict systemic redundancy. The logistics matrix is designed to instantly reroute resources. If a primary distribution center in Texas is knocked offline by a hurricane, the algorithm automatically triggers secondary and tertiary nodes to absorb the kinetic load, deploying emergency truck fleets from neighboring states. It is a decentralized network designed to absorb localized failures without ever interrupting the final output of the perfect burger. When you enter a McDonald's, you are stepping into a highly calibrated optical environment. The iconic red and yellow color scheme is not merely branding. It is a calculated deployment of specific electromagnetic wavelengths. In human biology, the frequency of red light stimulates the heart rate and creates a sense of urgency, while yellow triggers the release of metabolic hormones associated with appetite. This combination forces a subconscious biological reaction. You are not just deciding to eat. The exact spectrum of light bouncing off the walls is actively hacking your neurochemistry, accelerating your hunger and your internal clock. In a standard restaurant, chairs are designed to retain customers. In McDonald's, seating is an exercise in hostile ergonomics. The goal of the empire is maximum table turnover. To achieve this, the classic fiberglass and hard plastic chairs are engineered with specific rigid angles that provide zero lumbar support. The dimensions physically force the human spine into a posture that is tolerable for eating, but becomes acutely uncomfortable after exactly 15 minutes. The furniture does not ask you to leave. It initiates a physical kinetic eviction process, utilizing your own skeletal fatigue to clear the table for the next transaction. The physical environment is finely synchronized by an acoustic algorithm. The background music in a McDonald's is not an artistic playlist. It is an algorithmic metronome. During peak rush hours, the system deploys high BPM, beats per minute, audio tracks. Human psychology is deeply susceptible to rhythmic entrainment. This fast-paced acoustic data subconsciously dictates the speed at which customers chew their food, swallow, and walk. Combined with bright, clinical lighting that eliminates shadows and privacy, the architecture itself acts as a massive, invisible centrifuge, constantly accelerating human mass in one door and out the other. A modern McDonald's is no longer just a physical structure. It is a sensory node in a massive artificial intelligence network. Before a customer even speaks their order, the machine is already tracking them. The drive-thru acts as a digital checkpoint, utilizing geofencing and license plate recognition to identify returning customers. Simultaneously, the neural network pulls in massive streams of environmental data, local traffic density, time of day, and even micro changes in the weather, such as a sudden drop in barometric pressure. The restaurant isn't waiting for you to arrive. It is actively watching you approach. This data is fed into a predictive machine learning algorithm. Its goal is not to process orders, but to mathematically predict the future. By analyzing the variables, the AI can calculate the statistical probability of exactly what will be ordered in the next 5 minutes. If the temperature drops below freezing and traffic is slow, the algorithm knows coffee and heavy burgers will spike. It sends a digital command to the kitchen display system to begin searing meat and dropping fries before the customer even rolls down their window. They have eliminated wait times by cooking for a probability before the words are even spoken. But the AI doesn't just predict behavior, it actively manipulates it. The digital menu boards outside are not static posters, they are dynamic interfaces connected directly to the kitchen's telemetry. If the system detects that the grill station is overwhelmed and falling behind, the algorithm will instantly alter the drive-thru display. It will remove burgers from the visual hierarchy and heavily promote chicken nuggets to steer customer choices, balancing the kinetic load on the kitchen staff. You think you are making a free choice, but your decision was algorithmically guided by a neural network optimizing its own internal workflow. The universe naturally tends toward chaos. In the food industry, this is known as biological entropy. Meat varies in fat content, potatoes differ in moisture, and human labor is inherently inconsistent. The ultimate engineering achievement of McDonald's is not culinary. It is its absolute victory over organic chaos. By deconstructing food down to its molecular and thermodynamic components, they stripped away all variables. They replaced the art of cooking with the inflexible clockwork of physics, thermodynamics, and industrial manufacturing, forcing nature to bend to a strict mathematical equation. A brilliant system is useless if it cannot be scaled. McDonald's succeeded globally because the laws of physics do not change across borders. A highly calibrated Venturi valve works identically in France as it does in Brazil. The specific heat capacity of their frying oil ensures the exact same cryogenic shock in every country. They did not export a recipe. They exported a rigid, unyielding physics engine. This global calibration guarantees that millions of times a day, across different time zones and cultures, the exact same Maillard reaction occurs, producing a physically identical output. The McDonald's machine never sleeps and never stops running. It is a continuous loop of thermal transfer, fluid dynamics, and algorithmic logic. It is the ultimate manifestation of industrial engineering applied to human sustenance. Thank you very much for watching. If you made it to the end, it means you truly appreciate a deep engineering approach to everyday systems. Please take a second to hit the like button and subscribe to the Simply Explained channel. Until next time.